Your brain is literally rewiring itself right now as you process these words. And here's what's fascinating: that same neuroplasticity that's allowing you to learn is the exact mechanism that created your self-doubt in the first place. And it's the same mechanism we're going to use to eliminate it permanently. Self-doubt isn't just an inconvenient feeling, it's a learned neural pattern that hijacks your prefrontal cortex, floods your system with stress hormones, and literally shrinks the areas of your brain responsible for decision-making and creative thinking. The fundamental breakthrough in understanding self-doubt comes from recognizing that it operates through the same neural mechanisms as any other learned behavior. When you experience self-doubt repeatedly, you're literally strengthening specific neural pathways through a process called long-term potentiation. Each time you hesitate, second-guess yourself, or catastrophize about potential failure, you're reinforcing synaptic connections that make these responses more automatic and more likely to occur in the future. What's remarkable is that this process is completely reversible. Your brain maintains neuroplasticity throughout your entire life, meaning those doubt-generating neural networks can be weakened while confidence-building pathways are strengthened. This happens through a complementary process called long-term depression, where unused neural connections literally atrophy and disappear. The key lies in understanding that your brain doesn't distinguish between imagined and real experiences when it comes to neural pathway formation. Every time you visualize yourself succeeding, taking action despite uncertainty, or handling challenges effectively, you're creating the same neural firing patterns that would occur if you were actually performing these behaviors. This is why mental rehearsal is so powerful. You're literally practicing confidence at the neurological level. Research in cognitive neuroscience has shown that it takes approximately 63 days of consistent practice to establish new neural pathways strong enough to override existing patterns. This isn't arbitrary. It's the time required for myelin, the fatty substance that insulates nerve fibers, to fully develop around new neural connections. Once these pathways are myelinated, they become the brain's default response pattern. The process works through three distinct phases. First, there's the destabilization phase, where old neural patterns become neurochemically labile and open to change. This typically occurs during the first 2 weeks of implementing new protocols. Second is the reconsolidation phase, where new patterns begin forming while old ones weaken. This spans roughly weeks 3 through 6. Finally, there's the stabilization phase, where new neural pathways become fully myelinated and automatic. Understanding this timeline is crucial because most people abandon new practices during the destabilization phase, mistaking the temporary discomfort of neural rewiring for evidence that the process isn't working. But this discomfort is actually proof that neuroplasticity is occurring. Your brain is literally restructuring itself to support new patterns of thinking and behavior. Your dopamine system operates as a sophisticated prediction machine, constantly calculating the difference between expected and actual outcomes. This isn't just about feeling good. Dopamine serves as your brain's primary learning signal, determining which behaviors get reinforced and which get abandoned. When reality exceeds expectations, dopamine neurons fire in bursts, creating what neuroscientists call a positive prediction error. This surge doesn't just feel rewarding, it literally rewrites your neural circuitry to increase the likelihood of repeating the behavior that led to the unexpected success. The traditional approach to goal setting actually sabotages this system. When you set expectations at your maximum potential, hoping to achieve 100% of what you think you're capable of, you're setting yourself up for neutral or negative prediction errors. Even when you perform well, achieving 85% or 90% of your goal registers as a failure in your dopamine system, regardless of objective success. This creates a cascade of neurochemical changes that reinforce self-doubt patterns. The 20% calibration isn't arbitrary. It's based on extensive research into optimal prediction error generation. This percentage creates a sweet spot where you're likely to exceed expectations while still maintaining genuine challenge. When you consistently experience positive prediction errors, several neurobiological changes occur simultaneously. First, your ventral tegmental area begins releasing more baseline dopamine, elevating your general motivation levels. Second, your nucleus accumbens becomes more sensitive to reward signals, making you more likely to recognize and celebrate small wins. Third, your prefrontal cortex develops stronger connections to reward centers, improving your ability to maintain motivation during challenging periods. This protocol also activates what researchers call the dopamine ramp. Instead of experiencing a single spike when you achieve your goal, you get multiple dopamine releases throughout the process when you set the calibrated expectation, when you begin making progress, and when you ultimately exceed the target. This creates a self-reinforcing cycle where the act of pursuing goals becomes intrinsically rewarding, independent of external validation. The neurochemical impact extends beyond motivation. Dopamine plays a crucial role in neuroplasticity itself, making your brain more adaptable to learning new patterns. Higher baseline dopamine levels increase the production of brain-derived neurotrophic factor, a protein that promotes the growth of new neural connections. This means the dopamine prediction error protocol doesn't just make you feel more confident, it literally makes your brain more capable of learning confidence-building behaviors at the cellular level. The anterior cingulate cortex operates as your brain's alarm system, processing both physical pain and social threats through identical neural pathways. This evolutionary overlap explains why public speaking can literally feel as threatening as physical danger. Your brain cannot distinguish between a saber-toothed tiger and a judgmental audience at the neurochemical level. Both activate the same stress response cascade, flooding your system with cortisol and adrenaline while simultaneously impairing higher-order cognitive functions in your prefrontal cortex. Controlled stress exposure works by systematically training this alarm system to respond more appropriately to non-life-threatening challenges. When you deliberately expose yourself to manageable stress while maintaining cognitive control, you're teaching your anterior cingulate cortex to differentiate between actual danger and mere discomfort. This process, known as stress inoculation, creates lasting changes in how your nervous system interprets and responds to challenging situations. The key lies in the controllability factor. Research shows that when stress is predictable and escapable, it actually strengthens neural resilience rather than depleting it. Cold exposure exemplifies this perfectly. The physiological stress is intense, but completely safe and time-limited. During cold exposure, your sympathetic nervous system activates dramatically, but because you maintain conscious control over the experience, your prefrontal cortex learns to regulate this activation rather than being overwhelmed by it. This training creates measurable changes in brain structure and function. Regular controlled stress exposure increases the thickness of your prefrontal cortex while reducing the reactivity of your amygdala, the brain's fear center. It also enhances communication between these regions, allowing your rational mind to more effectively modulate emotional responses. Additionally, the practice increases production of norepinephrine, a neurotransmitter that sharpens focus and attention while building resilience to future stressors. The neuroplasticity extends beyond stress response. Each time you maintain composure during controlled discomfort, you're strengthening what neuroscientists call cognitive control networks. These are the same neural circuits responsible for self-regulation, decision-making under pressure, and maintaining confidence in challenging situations. The skills transferred directly. Someone who can breathe calmly while immersed in ice water has trained the exact neural pathways needed to remain composed during a high-stakes presentation or difficult conversation. Most importantly, this protocol builds what researchers term stress-related growth. Instead of viewing challenges as threats to be avoided, your brain begins categorizing them as opportunities for neuroplastic adaptation, fundamentally shifting your relationship with discomfort from avoidance to engagement. The discovery that social rejection activates the same neural networks as physical injury represents one of the most significant breakthroughs in understanding human behavior. When researchers used functional magnetic resonance imaging to scan brains during experiences of social exclusion, they found identical activation patterns in the anterior cingulate cortex and right ventral prefrontal cortex, the exact same regions that light up when someone experiences physical pain. This isn't metaphorical. The neurochemical response to criticism, rejection, or social threat is literally indistinguishable from the response to physical harm. This overlap exists because social connection was crucial for survival throughout human evolution. Being ostracized from the group meant death, so our brains evolved to treat social threats with the same urgency as physical dangers. The problem is that this ancient system cannot adapt quickly enough to modern contexts where social disapproval rarely carries life or death consequences. Your brain still interprets a challenging question during a presentation as a survival threat, triggering the same physiological cascade that would help you escape a predator. Understanding this mechanism transforms how you can approach self-doubt. Instead of viewing it as a character flaw or emotional weakness, you can recognize it as a predictable physiological response that follows specific neural pathways. This reframing is therapeutically powerful because it shifts the locus of control from your personality to your neurobiology, and neurobiology ology can be trained and modified through targeted interventions. The physiological nature of social pain also explains why traditional positive thinking approaches often fail. You cannot simply think your way out of a neurochemical response any more than you could think your way out of physical pain. However, you can train your nervous system to respond differently through the same principles used in physical rehabilitation. Just as physical therapy gradually increases tolerance to movement after injury, you can systematically increase your tolerance to social discomfort through graduated exposure and conditioning. This understanding also reveals why certain interventions work so effectively. Acetaminophen, commonly known as Tylenol, has been shown to reduce the intensity of social rejection just as it reduces physical pain, because both types of pain share the same neural substrate. More importantly, techniques that work for managing physical pain, such as controlled breathing, progressive muscle relaxation, and mindfulness, are equally effective for managing social anxiety and self-doubt, because they target the same underlying neurophysiological processes. Your sense of identity exists as a complex neural network distributed across multiple brain regions, with the medial prefrontal cortex serving as the primary hub for self-referential processing. This network constantly updates based on the evidence you feed it, but here's the critical insight. Your brain gives disproportionate weight to information that confirms existing beliefs about yourself. This cognitive bias, known as confirmation bias, means that if you currently identify as someone who struggles with self-doubt, your brain will automatically filter experiences to reinforce this narrative while overlooking contradictory evidence. The retrospective validation framework exploits a fundamental principle of memory consolidation called the recency effect. Information processed most recently has a stronger influence on neural pathway formation than older memories. By systematically documenting instances of courage and capability at the end of each day, you're ensuring that these positive data points become the most neurologically salient information your brain processes before sleep, the period when memory consolidation is most active. The specificity requirement isn't arbitrary. It leverages how your brain encodes episodic memories. Vague statements like, "I was confident today," don't create strong neural impressions because they lack the sensory details that make memories neurologically sticky. However, when you write, "I presented my budget proposal," despite feeling nervous about the Q4 projections, you're encoding multiple sensory and contextual details that create rich neural representations. These detailed memories become more easily accessible for future recall and more influential in shaping your self-concept. This practice also activates what neuroscientists call the generation effect. Information you actively generate and articulate becomes more deeply encoded than information you passively consume. The act of identifying and writing down your moments of capability requires active neural processing that strengthens the associated memory traces. Each time you engage this process, you're literally building stronger neural pathways between your identity networks and memories of successful action taking. The three-instance protocol is based on research into optimal cognitive load for memory formation. 3 items represent the maximum number of complex pieces of information your working memory can effectively process simultaneously without cognitive overload. This ensures that each instance receives adequate neural attention while preventing the dilution that occurs when trying to process too many items at once. Over time, this daily practice creates a robust library of capability-based memories that your brain can access whenever self-doubt arises, providing immediate neurological evidence that contradicts doubt-based identity narratives. Your nervous system operates under strict metabolic constraints that govern how much neuroplastic change can occur simultaneously. Neuroplasticity is an energy-intensive process, creating new synaptic connections, producing neurotransmitters, and myelinating neural pathways requires significant glucose and oxygen consumption. When you attempt to change too many behavioral patterns at once, you exceed your brain's metabolic capacity for adaptation, leading to what neuroscientists call plasticity saturation. This results in incomplete neural changes that fail to stabilize into lasting behavioral modifications. The staged implementation approach leverages what researchers term sequential neuroplasticity, where one set of neural changes must consolidate before the next set can effectively begin. Each protocol targets different neural networks, dopamine pathways, stress response systems, and identity networks, but these systems are interconnected through complex feedback loops. Attempting to rewire all three simultaneously creates competing demands for limited neural resources, often resulting in interference patterns that prevent any single change from fully establishing. Research in motor learning provides the clearest evidence for this principle. Studies show that when people attempt to learn multiple complex skills simultaneously, they achieve significantly slower progress and lower retention rates compared to sequential learning approaches. The same principle applies to behavioral change because habits and confidence patterns are learned through identical neural mechanisms as motor skills. Your brain treats confidence-building protocols as complex behavioral sequences that require the same methodical approach as learning to play piano or mastering a tennis serve. The weekly timeline aligns with natural cycles of neural adaptation. Initial neural changes begin within 24-48 hours of practicing a new behavior, but stabilization requires approximately 7-10 days of consistent repetition. This stabilization period involves multiple neurobiological processes, strengthening of synaptic connections through long-term potentiation, increased dendritic branching to support new neural pathways, and gradual myelination that makes these pathways more efficient and automatic. Beginning a second protocol before the first has stabilized creates what neuroscientists call retroactive interference, where new learning disrupts the consolidation of previous learning. However, introducing the second protocol after the first week leverages positive transfer, where established neural changes actually facilitate the acquisition of related skills. This creates a compounding effect where each subsequent protocol becomes easier to implement because your brain has already developed some of the underlying neural infrastructure required for behavioral change. The staged approach also prevents the psychological phenomenon known as change fatigue, where the cognitive demands of multiple simultaneous modifications deplete mental resources and reduce motivation for continued practice. The transformation starts now, not when you feel ready, not when the conditions are perfect, but right now with the next decision you make. Choose one protocol from today's video and commit to practicing it for the next 7 days. Your future self is counting on the neural changes you create in this moment.